Yeah, so thanks everyone for coming to this reading group. Vincent and I are gonna cover the basics and advances of diffusion score-based generative models and talk a bit about their connections. So this is a promising research direction for generative modeling, where we learn score functions on a large number of noise-perturbed distributions and then generate samples with Langevin dynamics. So next slide, please. Yeah, here's the outline of the talk where I will present generative modeling by estimating gradients of data distribution. And then Vincent will present the denoising diffusion probabilistic models. And then Tor will talk a bit about score-based generative modeling with stochastic differential equations. Next slide, please. So what is generative modeling? Well, suppose that we are given a set of IID data points sampled from some unknown underlying data distribution. The goal of generative modeling is to model this data distribution so that we can, for example, generate high quality new synthetic data points by drawing samples from this distribution, or compute the probability of a data point coming from this distribution. And this is particularly a challenging task if we want to be able to handle complex and high dimensional structured data, such as high resolution images and audio waveforms. So next slide, please. So in the first part of this presentation, I'm going to tell you a bit about the basics of score-based models and cover this paper by Song and Ermer. Next slide, please. So in an earlier reading group, we learned that an energy-based model represents a probability density function by modeling its energy function f, which in a machine learning context is typically a flexible and unconstrained neural network that outputs a scalar. EBMs are super flexible probabilistic models, but they have an intractable normalizing constant z that depends on the parameters theta, which prevents us from training the model using maximum likelihood estimation. One popular approach to dealing with this intractability is to instead learn the true data score function, which is the gradient of the log density with respect to the input variable x. The idea is to use the score-based model S to learn the true data score function. And the good thing about this approach is that the score of an energy-based model is just the negative gradient of the energy function, and it is independent of its normalizing constant, which significantly expands the family of flexible models that we can tractably learn. So one interesting thing is that unlike earlier work on energy-based models, recent works construct generative models by directly modeling the score function S rather than the energy function f. Although such unconstrained score-based models are not guaranteed to be the gradient of any function, in practice they perform better than explicitly differentiating a parameterized energy function. So anyway, in this talk, we'll only consider unconstrained score-based models. So next slide, please. Score-based models are trained by score matching, which minimizes the Fisher divergence between the true data score and the score-based model. This objective works for non-degenerate data distributions because in this case, two probability density functions have identical score functions, if and only if they're identical. However, score matching is infeasible and problematic in practice. So firstly, since the true data distribution is unknown, we cannot evaluate the true data score term in the score matching objective. Also, by the manifold hypothesis that real-world high-dimensional data lies in a low-dimensional manifold, the log data density is undefined for many input x, where the true data score is also undefined. But fortunately, there exists a family of approaches that make score matching practical. So next slide, please. In this talk, we'll focus on denoising score matching because it relates to more advanced score-based models and diffusion models that will be introduced later. The idea of denoising score matching is to corrupt the true data distribution with, for example, Gaussian noise. The corrupted data distribution is well defined for every input x. And most importantly, it turns out that the resulting objective does not require us to evaluate the true data density function, which makes it practical. The major drawback of adding noise to data is that the corrupted data distribution is no longer equal to the true data distribution. So the denoising score matching objective is not the same as the original score matching objective. But in practice, this is fine as long as the perturbation noise level sigma is small enough so that the corrupted data distribution is close to the original data distribution. Next slide, please. So once we train the score-based model, the next thing we want to do is to sample new data points from it. There is a type of iterative sampling procedure called Langevin dynamics, which gives us an MCMC procedure to draw samples from a distribution using only its score function. So specifically, the chain starts from an initial point x0 from an arbitrary prior distribution pi, and then iterates equation 1. So it turns out that the chain converges to a sample from the target distribution as epsilon goes to 0 and k goes to infinity. In practice, the error is negligible if epsilon is sufficiently small and k is sufficiently large. So we can just substitute the true data score with a learned score-based model in equation 1 and to draw approximate samples from the data distribution. So next slide, please.
There we go.
Yeah, this slide shows a visualization of Langevin dynamics for a mixture of two Gaussians, where the contour lines represent the density function and the vector field represent the score function. So you can see that Langevin dynamics accesses the distribution only through the score function and moves points towards the gradient direction with some noise. Okay, next slide, please. So far, we've talked about how to train and draw samples from score-based models. But since naive models have limited successes in practice, the key challenge is that estimated score function is inaccurate in low-density regions because very few data points are available for training the score-based model. This makes things problematic when we draw samples using Langevin dynamics, because for high-dimensional data, the randomly initialized points of the chain is very likely to be in one of the low-density regions with unreliable estimated scores, which jails Langevin dynamics from the very beginning stage, and so prevents us from generating high-quality samples that are representative of the true data distribution. Next slide, please. So our first attempt to address this issue is to use denoising score matching with a large perturbation noise sigma, which populates data to low-density regions. This requires sigma to be sufficiently large so that we can corrupt the data distribution that they cover the low-density regions. However, remember that sigma should also be sufficiently small so that the denoising score matching objective does not deviate from the original score matching objective too much. But unfortunately, it's almost impossible to balance this trade-off in practice. Next slide, please. So Song and Ullman proposed to instead perturb the data distribution with multiple noise levels, sigma 1 to sigma L, given by a geometric progression, with sigma 1 being sufficiently small, sigma L being sufficiently large, and the number of noise levels L being hundreds or thousands. In this setting, we estimate the score functions of all corrupted data distributions with a single noise conditional score network, which takes an additional variable sigma as input. So this gives rise to a training objective, which is a weighted sum of the individual denoising score matching objectives at different noise levels. The weighting function lambda I in this objective is typically chosen to be sigma I squared because it makes sure that every individual objective in the sum has a similar scale. So next slide, please. To sample from this model, we employ a procedure called annealed Langevin dynamics, which combines a sequence of Langevin chains with gradually decreasing noise levels. For example, in the animation shown in this slide, we first draw samples from sigma 3 corrupted distribution using Langevin dynamics, starting from randomly initialized points, and then use these samples as the initial points when drawing samples from the sigma 2 corrupted distribution using Langevin dynamics. And then we repeat this process until we obtain samples from sigma 1 corrupted distribution, and then we use these samples as the sample from the score-based model. So next slide, please. This slide showed how annealed Langevin dynamics generate images, which actually resembles the reverse of a diffusion process. So Vincent will talk about diffusion models and make connections.
Yes, hi. So please interrupt me if you have any questions. I'm going to talk about denoising diffusion probabilistic models, which at first sight, when it was introduced, had quite little connection with what Wenlin just presented. But as you will see, the connection is actually pretty strong. And I'll try to highlight this in the equations as well. So next slide, please. So before I dive in, I want to give you a bit of history, how these things actually connected and how these things were developed, because I think it's quite interesting to see how from two different angles people actually derived to the same objective. So Wenlin just went over this 2019 paper in which they introduced score matching on noisy objectives, on noisy distributions, and they used Langevin dynamics to sample from the distributions. So back in 2015, Sol-Dickstein introduced denoising diffusion probabilistic models through a variational objective. So quite a different setup. However, 5 years later, in 2020, Ho et al. Made great improvements to Sol-Dickstein's work. They actually made it work for the first time on difficult distributions like images. And they showed that this elbow objective from 2015 is actually quite similar to the score matching objective from 2019. So this is why the first connection between these two methods were drawn. And then we have the last paper, which Thor will present mainly. So Song et al., who basically collaborated with the people from the 2015 paper, who further continued to work on the unification and showed how these Langevin dynamics can also be used in denoising diffusion probabilistic models. So next slide, please. Yeah. So what is a diffusion process? I'm gonna go back way to the start of this 2015 people and introduce you the basics. I'm gonna focus a little bit more on the mathematics because I think some of these derivations are quite elegant and they are not in the paper. So maybe this will help you when you actually dig through the paper to actually understand what is going on. So the diffusion process in itself, the forward pass is quite simple. So let's say at time step t, we start with a known distribution, this Swiss roll, for example. What we then do, the known the data distributions here and the forward pass are denoted by a Q letter. I'm following the notations from the paper. So at time step t, we have a known distribution, this Swiss roll, and then we gradually add noise to these data points up until we end up with Qx capital T, where we basically end up with a white Gaussian noise. Mathematically, this is given below here, where we write down this Markov chain, where we specify how we corrupt each of the data, each of the samples by some diffusion rate beta T. And yeah, next slide, please. So this was the forward pass, now the reverse. So in the reverse, we start with white noise and we want to go all the way back to the sample from our data distribution. Obviously, this distribution is not known. So what we do here is we parameterize this by a Gaussian distribution where we have some mean and some covariance. So what I've written down here is the backward pass where we have P of theta to show you that this is a parameterized distribution where we know the previous or the next latent variable, and we want to have a distribution over the previous one. So we go backwards in time if you like. I also indicated by this dashed line what the forward process does. So the forward process adds noise. The reverse process tries to denoise this sample again. And as I said, we have no closed form solution to this denoising, to this reverse process. So we just for now parameterize them using Gaussians, where this mean and this covariance is simply given by neural networks. Next slide, please. So you can think of this model, of this denoising model, as a latent variable model, where the known variable are the samples from the true distributions Q of x0. And we can basically, if we want to have the density of this of a data point under our generative model, what we do is we integrate out all the latent variables. So different to variational autoencoders, typically where your latent variables are lower dimensionals and you have only one per data point. Here we have t-1 latent variables per data point, and they are of the same dimension as our as the dimension of our data. So indeed, if we want to have the probability of our data point under our generative model, what we do is we simply integrate out all the latent variables. So you can see how this in the stop integral we basically integrate out all the gray variables, right, from 1 up to t. And as I've said, in order to given this reverse model, we can actually draw samples at x0 by simply traversing the chain backwards. So we start by sampling white noise, which is a known distribution, and then we follow back. We go backwards in the chain by evaluating this neural network with this trained mean and covariance. So this is fairly straightforward, but I guess the main question is how do we actually train this neural network? How do we train the weights of this mean and this covariance? And this is what we're going to do next. In order to do this, though, we need two properties of this forward chain. And again, this is not really well specified in the papers, which is why I spend a bit more detail, which is why I want to spend a little bit more time on it here. So maybe it will help you when you read the papers. So the first property of the forward diffusion process that we will use is the fact that we can draw a sample at time step t without actually going through the chain. So this is in the forward process. So I start by giving you the definition. So given the previous latent variable, the next one is simply given by perturbing the previous one, right? This is the first equation. We can reparameterize this using the typical Gaussian reparameterization trick, where we add some noise to the mean. And then we can basically like unroll this. We can repeat this trick for xt minus 1 and do this all the way down up to x0, because all of these little noise perturbed variables ZTs are independent. We can simply sum the variances and we end up with a distribution over xt given x0, which is again Gaussian, and where the mean is given by the product of all the alphas, which is basically the size or the diffusion rate you added at each of the steps. Next slide, please. So this was the first property, and we have the second one, where conditioned on x0. So what we basically want to do now is we want to analytically specify one of the backward steps. So doing this directly is impossible, but when we condition on x0 on the first latent variable or on the data itself, this actually becomes tractable. So conditioned on x0, the reverse conditional probability becomes tractable. And I'm not going to go into too much detail here, but basically this is simply applying Bayes' rule. So the first term there is exactly the definition that we had, and then the factor that we have there is the first property that we used. So we end up with something that is Gaussian 3 times, and there are known analytical solutions to this. So we can summarize this backward pass. So q xt minus 1 given the next one and the first one as a new Gaussian, where we have an analytic mean and an analytic variance. This will be very handy in the next slide. So as I've said, we want to train these weights, right, of the reverse pass. And the way we do this is by using the typical maximum log likelihood method, where we want to maximize the density or the probability that our model gives to the data. So this is exactly p of theta x0. I'm going to go very briefly through these things. So in the first step, we simply integrate out all the latent variables. In the second step, we multiply and divide by our forward process conditioned on x0. In the third step here, this is for typical Jensen inequality, where we take the logarithm inside of the integral, and we take the expectation over the forward pass. In the last step, this is again quite simple, is we basically write down the forward and the backward pass, and we write it down as the sum over time, the sum over the different steps. So this is the elbow, and this is actually all tractable, right? So the first log over p of xt is simply the log over a Gaussian distribution, which is something that we have. And we also have the two terms in the sum. However, in the original 2015 paper, they continued a bit to reduce the variance of this elbow. This is what we do in the next slide. So in here, I simply repeated the last term of the elbow. And then we use a second property where we can condition on x0 to get a closed form for xt minus 1. And filling this in, we basically reduce the variance of the elbow, and we end up with the final KL. Next slide, please. We end up with this scale, and this was, or with this elbow, sorry. And this was the one which they arrived at in the original 2015 paper. So far, there's actually quite little connection with what Wenlin has presented. However, so in this scale, everything is analytic, and we can compute this in closed form. And the results that they obtained with this were quite all right, but not as impressive as what we see currently with GANs and what with the generative models that Wenlin presented. So basically, we had to wait for 5 more years. And the next slide, please.
Vincent?
Yep.
I thought it might be a good time to just slow down a bit and just take stock. So maybe I'll ask some questions, but
yep,
mainly for
thank you.
I guess. So maybe we could sort of start. So you presented this sort of I guess the way around they do it in the paper, where you start with a data distribution, you think about corrupting it with noise and going back up to the top. But maybe we could sort of take a more sort of standard modeling approach as well, and first think about just the model that you specified, and then doing approximate inference in the model. So you specified a sort of a conditional Gaussian hierarchical model, which starts off with Gaussian noise and maps it through a set of Gaussians where the statistics depend on the previous, the mean and the covariance depend on the previous state of the latent variables to get down to the data distribution of the model.
Yeah, exactly.
The outputs. Then you've written down a standard elbow. So nothing surprising at that point, I guess. And then the sort of, is it fair to say the trick here is, like, normally when we write down Q distributions, we use some approximate Q that, we've parameterized a family and we do optimization within that family. Whereas here, the Q is going to be generated by this like reverse Gaussian corruption process. So you're using a sort of a more constrained Q that's coming from, that you can think about in terms of this data corruption process. Is that the sort of the right way to think about it?
Yeah, so I also tried to frame it in this way, but I didn't manage. And the funny thing is that, so I followed the notation from the paper, and they actually use Q for the forward process and P of, so they don't use the Q like the one we use to have like an approximated or a restricted variational distribution that we try to minimize the distance from the true distribution.
Yes. So
in this perspective, the notation is super confusing in this original paper, because here Q is actually the forward process.
Right.
P of theta is our approximating distribution of the reverse pass. But the interesting thing is, like, and yeah, thank you for interrupting me, because there's actually much more to tell about this equation, is especially the middle KL term here. So the KL between the Q of xt minus 1 and P of theta xt minus 1, right?
Yeah.
What we're basically trying to do here is trying to minimize the distance between two distributions. One is the one where we go forward, and the second one is the one where we go backward. But in a sense, if we make these little steps, the steps at which we add noise small enough, it kind of makes sense that these two distributions have to be similar, right? So it's framed as an elbow. It's framed like in a variational autoencoder, if you like, by minimizing this, by optimizing the log likelihood, by introducing this extra distribution. But it's not exactly minimizing a distance from the true posterior. It's more like minimizing the distance between the forward and the backward pass by making the step small enough. And then it kind of makes sense that these distributions have to be similar.
Great. Could you just get back one more slide? Maybe we could just talk through this in a bit more.
Maybe one more, actually.
Yeah, one more. Yeah.
So typically what you do here, well, in VI at least, here you introduce the approximation, right? Like you introduce your Q of your variables. But what we're doing here is we actually multiply and divide by the forward process, which in the paper, confusingly, they use it as a Q for.
Yeah. I'm certainly happy with your notation. I don't think I have a problem it's true that Q comes from this slightly funny construction, but Q can be anything here, so we're sort of happy with that. I'm sort of made my peace with that.
Yeah.
Cool. Okay. I think I'm happy now. Are there any other questions at this point? Might be a good chance for other people to ask questions.
I have I have one question. It's about the PXT that appears here.
Yep.
What is the exact form for this? I assume that is the distribution that you obtain at the end of the process that adds noise. No?
Yeah, I didn't add the theta here because we assume this is a known and this is Gaussian, for example, like white noise.
And yeah, so the reason for this is that the effect of the initial data distribution vanishes.
Exactly.
Okay, and you have the exact form for, I assume that this would be like Gaussian, for example. Do you have then the exact form for the means and variances of this?
Yeah, we do. So we know the exact one for P of theta because we parameterize it to be a Gaussian, right? Mm-hmm. And then the Q one where we go forward in time is also given by Gaussian, where we corrupt them by noise, right?
But I assume that this depends on the statistics of the initial data distribution somehow. There should be something affecting there. I mean, at least just the marginal means and variances.
Yeah, it does. Yeah, it does. So you'll see in the, I guess in 2 or 3 slides that the way we parameterize them shows you that it also is affected by x0, like the initial data point.
Okay.
Just sorry, one quick question. I was just on terminology for terminology here. When you're describing the forwards pass, the diffusion through the Q process, is that, am I correct in that that's kind of like the opposite? Normally when I think of the forwards pass through a model, I think of the data generating process. So like if it's a VAE, say, you'd sample some latent noise and then pass it through your neural network to get the structured data. So I guess the terminology wise, like their forwards pass is kind of like, is it kind of like the inference pass in a VAE? Like it's kind of going from data to noise, as opposed to what I think we think forwards pass as being, which is noise to data.
Yeah, exactly.
Is that correct?
Yeah.
Okay.
Exactly. So in the backward pass we go from noise to data, and in the forward pass we go from data to noise. Yeah. And in VE is exactly the opposite, indeed.
Cool. Thanks.
Yeah, thank you very much for the questions. So I hope up until this point things are more or less clear, because what we're now going to do is basically going to simplify this. And then after the simplifications, we will see how the connection, or at least the close similarity between the 2 objectives and between the 2 methods. That's kind of the remaining of my slides. So in the next slide, we make the first simplification, and this is the work by Ho et al. So 5 years after this first paper. So the first thing they do is they fix the diffusion rates. So they fix the levels of noise that we add at each of the levels. And by doing this, the first term in this elbow that we had is basically constant with respect to the parameters because they aren't any. So like Miguel said, this PXT here is just, it's not parameterized. We just assume it's Gaussian, it doesn't depend on the data. And then we have the forward process given x0 indeed is also just it's not parameterized basically. So we can drop it from the objective is the main conclusion. Next slide, please. All right, and then going forward, so this is the way we parameterize in the top equation. This is the way we parameterize our backward pass, right? So again, some Gaussian with a mean and a variance. Any questions? No. And basically what they say in this paper is, let's fix this covariance in the backward pass to be the same as the one in the forward pass. And again, this kind of makes sense if you take your step sizes small enough that these 2 variances are similar. And they actually try two things in this paper. They try to fix it to the same as in the forward pass, and they also try to fix it to the optimal value of this conditional backward pass, but doesn't matter too much. But basically they set it to two extreme values. The first one is optimal in the case that our data distribution is given by a Gaussian. And the second one is optimal when our data distribution is quite extreme to be given by a single point. So they basically specify to these two extreme values. And what they saw is that it doesn't matter. The sample quality is very similar to equal, independent of which extreme case they pick. And in the second slide, they basically, the second slide explains why it is the case. So what I'm showing you here is the ratio of these two variances. So this is beta tilde over beta t. So these are the two extreme cases. And what we see is that for most of the steps, they're basically the ratio is 1, which means these two quantities are the same, which also explains why setting it to either of these two extremes doesn't matter too much, because for most of the time, they're exactly the same. This is kind of the key takeaway from this slide, is that it doesn't matter too much what we set this value to, which also hints at the fact that this is not a very principled method in many ways, right? If you can just specify value, it's two extreme cases, and it kind of works either way. The sample quality is the same. It doesn't matter too much. Without a real explanation why, at least not in the papers that we read. It's a little bit worrying.
Sorry, I just had a question regarding the site. So obviously it looks like in the first step or the last step in the reverse process, it will matter a lot, right? Because that's when you are generating your image, for example.
Yeah.
And so if you add noise, that's not going to recover, a perfect sample. So what's their workaround there?
Sorry, say that again.
So in the last step in the reverse process, right? You're generating the actual data point, the image. And if you have this larger variance, then that's not going to be a great sample. I think that's where the ratios are also different in the beginning of the plot.
Yeah. So in both cases, so indeed when you generate the data itself, the beta t there is quite small. So indeed the ratio is different, but they're small in both cases. Something they argue in the paper is that this last few steps are important for the log likelihood, at least. So it doesn't really matter too much in the sampling stage, because in both cases these values are quite small anyway. The ratio is different, but they are small. But it is more important when it comes to actually computing the log likelihood of a sample under your model.
Okay, thanks.
And next slide, please. All right, so this term, so the top term here is this KL was this middle KL that I showed you before, right? In the original objective. So here we're trying to minimize the backward pass and the forward pass. Without going into too much details, if we fill in the mathematics, what we end up with is an objective. This is given in the box here, which is basically exactly the same as the objective that Wenlin showed you in one of his slides. So this was quite a surprising result, is that how these two objectives will match each other. So this is, basically what you end up doing in practice is you draw a sample from the data, you draw a sample from white noise, and then you basically try to learn a neural network. So Z theta here is a neural network in which we input our corrupted data sample with the actual time, the timestamp. We try to learn a neural network that can predict what the noise was that was used to generate a sample. This is exactly the same objective that we actually end up doing when we do a denoising score matching. So the key takeaway, I guess, here is that both the denoising diffusion models and the score matching arrive at the same objective, but to two completely different ways. So one has a strong connection in variational inference, and to VEs, and the other one is inspired by energy-based models.
Vincent, could you say a little bit more about that? I think we sort of went through those slides quite quickly, but you know, in the score matching stuff, we had a network that was trying to predict the score, or we were trying to model the score, right? So how does that relate to this picture? And
so this Z theta here is the same as trying to. So this, I guess, the score here is the gradient, right? Is how you change your samples in each of the steps, right?
Yeah.
And this Z, in a sense, is also the noise that we had, and it's exactly the way we change our samples in each of the steps. So in both ways, we're trying to learn a neural network that can predict how we change our samples in each time step.
Okay. Is there a tight relationship to the score though, like the derivative of a log energy, or is that it's more that the objective ends up coinciding?
Exactly, the objective ends up coinciding. Yeah.
But the model is quite a different interpretation of the two models. Is that true? Or
yeah, I think that's exactly right. Also, which is why this history is interesting, right? Like the way these two models were set up are completely distinct, and in the original papers, there's even no mention between the two models. But then, if you basically write down the math and then you basically compare them one to one, they see this very strong connection.
I mean, in a way, I'm much happier with this interpretation of a model, because the original justification for the model in the original piece of work feels very flaky to me, that that it's not necessarily normalizable, like there's no constraints in there that it should normalize, that you're not constraining the model to be positive, like the score doesn't have to be consistent with an underlying density at all, like a derivative of a normalizable positive density. So in a way, that I sort of believe that the training scheme could provide decent samples, and I'm not massively happy with the interpretation of why it's a good model and the way we should think about that model. So in a way, I sort of feel happier that this would then give a rational interpretation for perhaps why that first method works, because now you do have a well-defined generative process which is normalizable and involves well-defined densities and things like that. Is that your take on it? Or
exactly, I also feel I understand this, at least the generative process here, better than in the previous one, which is why it's indeed quite interesting that in the end these two methods are optimizing the same objective, right? So you can basically, if you understand this one, you can understand why the other one works, but it's indeed less. Yeah, I mean, the score matching one is a bit weirder, right? Like, and also the fact that we're like, yeah, I think these different noise levels is quite a different interpretation to this one, and also like the maths, at least in here, at least in this stream of work, right? These three papers I mentioned in at the top is quite easy to follow. I find in the score matching ones, they make bigger jumps. But yeah, again, they arrive at the same solution, so I guess.
I have one question. So it seems here that Z theta in the bottom equation is related to mu theta on the top, but I don't see the connection clear right away.
Yeah, it's exactly related. They instead of trying to learn this mean, they try to learn how you corrupt the mean, and I didn't include the maths here, but it's a simple reparameterization of the objective. So
it would be the mean plus some noise, the Z theta, and that you're trying to predict that, the mean plus the noise.
Yeah.
Okay.
Yeah, but it's indeed related. So you could also just try to. So the reason this is interesting is because of this connection, right? This is also why they write it like this, because then it boils down to this score matching objective. But you could also just implement this by trying to predict the mean. The reason that I guess they did it like this is because this score matching stuff works so well, right? So the way you parameterize your neural network is quite important. So it's like a bit of a chicken and egg problem here. They saw that one thing worked well and they can actually reduce it to the other. So, but it's also just as well valid to try to predict the mean. Next slide, please.
Yeah, maybe one thing I was mentioned regarding the point that Rich made is that it seems like in practice, these like score match, like these processes that they use are fairly simple. Usually they're affine, which we'll sort of mention later. And so even if you sort of you're learning the score, but it ends up kind of being just it's more like the scaling factor or like an affine transformation that ends up like parameters of an affine transformation, right? So it's not in practice, I think. So it's kind of like learning a scaling factor or a mean for the shifting, the perturbations that you're making, I think. But yeah. Next slide.
Yeah, I think that's it for me, right? That's up to you, Tor. Thank you all.
Cool. So yeah, so now we sort of what the next step is looking at the paper called score-based generative modeling with stochastic differential equations from a bunch of the same people, which is the one paper that also was mentioned earlier. It's probably the people that had the 2015 paper and people who had the 2019 paper. And so the idea here is that sort of thinking about like as we spoke about earlier, we have a lot of these noise levels, and the question is kind of like what happens if we take them to infinity essentially. And so the idea is then to sort of take these discrete number of sigmas that we have, and then we replace it with a function, which is now mapping from a interval from 0 to some positive t to positive numbers. And then we consider these like infinitesimal perturbations, where there's a lot of this GT here multiplied by some infinitesimal noise. And so people have seen stochastic processes before. Sort of you can describe this using a stochastic process in like an SDE form. So we have a stochastic differential equation, and the idea here is similar as before, right? We want to sort of resample the initial, the x0 sample from the data, and then we want to propagate this forward in time using this sort of this SDE here. And so here, what we're doing is we're adding some deterministic, so we're shifting it by some deterministic amount depending on the current time step and the current position, and then we're sort of perturbing it with some noise here. And so we often refer to this F as a drift function and this G as like a diffusion coefficient. And hopefully people have seen something like this before. And yeah, so, and if you haven't, there's probably useful to look at how you would solve one in discrete time. And so one sort of very standard scheme is this Euler-Maruyama scheme. And so what you do here is that you take your xi, which is like the next position, and then you define this by sort of taking the current position, and so now in discrete time, and then you add in the drift function evaluated the current position plus and the current time, and then you sort of take one small time step. So this is kind of your step size in this integrator, and then you perturb it by some Gaussian noise, which is scaled by the time step. And anyways, the time step is then decided by this t, the time of the sort of terminating state, divided by the number of scales that we have. And so now we went to this, we considered this fact of like going to the SDE formulation or the continuous case, and now we're just going back to the discrete one again. So it's very similar to what we had in the very beginning. We now have this like F here, and then we have this G here, and we're sort of thinking about, okay, we're sampling X0, and then we want to propagate it from the data, and then we want to propagate it forwards in time using some sort of, by perturbing it by some noise. And so we can still use this denoising score matching objective to train this method, similar as before, right? We have this same thing now. All we have is a different way of sort of parameterizing this PT here, essentially. It's still dependent on the fact that we have this PT in closed form, which is, it's another thing. But so we can compute this thing, which is just perturbing it, and then we have this S data that we're trying to learn, and then we'll get to how we can actually sample from this. It's very similar to the previous things where we do this reverse process. But it's a bit more tricky now because now we're working with SDEs rather than just sort of discrete version of it. And so here you can sort of see an example of how it looks, right? When now instead of just having a number of discrete, I mean, in practice, this is tons of discrete steps we're taking. It's not completely continuous since it's just we're working with computers here. But as you can see, it's sort of the intuition is that we have these stochastic processes and we have a bunch of these random paths going through time, and they go from something that's not normal to something that is kind of normal, like very noisy, right? Now you see the image doing the same thing. This is from this very, very nice blog post by one of the authors of the paper. And the neat thing with this framework, which I said, is kind of where that we first go to this continuous space, and then we just discretize it, and because we need to solve it and we need to solve it on computers, so we need to discretize it anyways. And the neat thing is that we can sort of take this continuous framing and then embed these existing methods and show that they sort of have they have similarities to them, and potentially also share ideas with them between them, as we'll see. But here's the first one, which is the SMLD, the score matching with Langevin dynamics that was introduced by that Wenlin spoke about earlier. And so here we have this, in this discrete time, we had it given by this thing. And so we had these, this was sort of how we defined this forward propagation of the noise, of the samples. So we were sort of sampling from x0, and then we were moving forwards in time using this sort of perturbation of the previous value. And in this paper, they show that this actually corresponds to this SDE that you can see here. So as you can see, this corresponds to this SDE that you can see here, and with this sigma t here. And this is, notice that it sort of doesn't have any drift coefficients. It's only drift function is only has this diffusion coefficient. I would say that I'm not showing the derivation here, but I'm not entirely certain like how. I think it's pretty much like an approximation rather a very natural correspondence. The reason why I say this is kind of naturally, at least what I expected, is that you will take this SD, and then you will use some discretization scheme, say Euler-Maruyama, and then you would go back to this sort of formulation that we saw in the previous paper when we didn't talk about SDEs at all. And then you can sort of, that's quite a natural approach of showing that this SDE actually goes, like this discretization is an approximation to this SDE here, right? But in the way they sort of do this is by, they pop in some delta t's here and divide by delta t into this integral here, and then they sort of argue that you have this term here divided by delta t, and if delta t goes to 0, you get something that looks like a derivative, and so on. So it's an approximation that is maybe not the most natural one, but it does seem to work well in practice, as I'll show you later. And so here we can sort of embed the Euler method into this SDE framework, which is quite nice. And
just a quick question about that. I think what you're suggesting would be very nice to show that it corresponds to a discretization of an actual underlying SDE, but aren't they rather arguing that the limiting case, like if you take the limit of their discrete case, then they would arrive at the SDE at the bottom, which is a bit different. Isn't that the difference between the two?
Yeah, so exactly, that's what they're arguing. As just like I'm saying, is like it's a bit at least like just by looking at it, I haven't spent too much time looking at the derivation of these things, but like by sort of briefly looking at it, sort of I guess you have to, to really make that rigorous, you have to make some arguments about, like, good arguments about the limiting case.
Yeah, and they probably didn't know their stochastic process theory that well, or didn't do it super well. Yeah.
I mean, I'm not going to say that, but because they probably know more than me. But my point is that it looked a bit like, there's probably a bit of waving of hands going on.
Yeah,
but it works fine. Right, we're trying to generate images and stuff anyway, so it's not a huge problem.
This version is the easy version, right? This is the linear direction where you're going from data to noise, right? This is where everything is linear. This is linear Gaussian thing, so it's almost completely uncontroversial, really.
Yes, indeed.
It's like this is the relationship between an autoregressive process and like a discrete time autoregressive process going to a Markov process in continuous time. It's exactly the same thing.
Exactly. So right now I'm only talking about the direction going from sort of p data to like some p prior, which is like, just like say something that looks like a Gaussian, right? So this is sort of going from the data to the just noisy, right? Just adding a bunch of noise to the data in a particular way.
Isn't that what we called Q earlier? Is that right?
Yeah, but it's a bit confusing because in this paper that Wenlin was talking about first, we didn't call it Q, and now we were calling it Q in the previous one. But yes, that's correct. Yeah. Any more questions about this? Cool. I'll move on. And just quickly, sort of one that's maybe worth pointing out, like there's one property about this SDE is that this is kind of, I guess, a nice thing about going to this SDE space is that they can sort of they can maybe analyze it in a bit different way. And so they show that the marginal variances sort of increases as with respect to time. And this is sort of like an element-wise inequality. And because of this, they refer to this as variance exploding SDE. So this is sort of the SMLD approach, corresponds kind of to like a variance exploding the SDE. I mentioned this because they will sort of use this terminology later on, and so I might as well put it in there. And then you can also show that the deep DPM, sort of denoising diffusion probabilistic modeling that Vincent was talking about, can also sort of be embedded in this framework. And they show that this SDE here actually corresponds. You can sort of view this discretization as an approximation to this SDE. In a similar way, it's it's probably a bit of waving of hands going on, but it works fine in practice. And now they're using this beta though, and yeah, now remember, but we're not using this sort of. So this also brings in the sort of connection between the DDPM approach and the sort of this SDE, this score matching approach. So I'm guessing here, but the here is more just about the model you're using. And they also show like a nice property about this is that if the sort of the initial the covariance of this variant preserving, they call it variance, this VP method, which is this SD here. If this is equal to the identity, then you're also going to have the identity covariance matrix at all other times going further on. And so they can refer to this as the variance preserving SD. Again, just terminology so you can understand what's going on later. So the DTPM is VP, and the SDLM, SDML, or whatever, is the VE. They also further sort of introduce this sub-variance preserving, sub-VP they call it. And the point here is that they're adding another term to this this original DDPM approach. And it has a property that is sort of always going to be upper bounded by this the variance, the covariance of the variance preserving SD that they showed. And so, you know, it's kind of nice in the sense that they can, they take these two different approaches, they convert them into like proximate SDs, and then they sort of construct a new method based on some properties that they inspect from the solutions to these SDs, and there's like it's kind of nice. But notice that it's not the methods that's like the coefficients are fairly simple, right? This beta here is like a linear interpolation. We're not doing something super crazy with the x's there. This is kind of what I was saying earlier, that these forward processes are generally not super complex when used in practice, though you could make them, but it's somewhat difficult computationally. And so just to sort of summarize these different methods, you kind of have this, here's the sort of the resulting conditional distribution of xt at given the x naught, which is going to be from the data distribution. So here you have this is, remember, this is the DLM, and this is the DDPM, and this is their sort of new version that they sort of introduced. And here you can see sort of the original, this discretized or original SMLD, SMLD, not SDLM, okay. The original discretization, and then you see the solution to the SD, the numerical solution to SD, and you can see that they match pretty nicely. And you can see the same thing for the DPM thing. So it seems like the limiting case analysis that it did seems to work well in practice, at least for the values of t that we have here. Any questions at this point? No, okay. Then I'll move on. So this was sort of what I mentioned earlier, like what's about when we want to go from the prior distribution or like this PT to the P data, right? How do we deal with this? And so it turns out that either actually for any sort of SD, you can find not any SD, there are some restrictions, but for most SDs, you can sort of find a nicely behaved SDs. You can find a reverse time SD, which has this form here. So here you see that the noise perturbations are the same, but now you have the different sort of drift function here, which involves the score. But remember that this is something that we'll be learning, so we won't actually need to compute this gradient, right? And this has the property that it will actually follow the path that is going forwards. It goes forwards in time. In this, it will be equal to that in distribution. That's stronger than sort of just every yt being equal to xt big T minus t in distribution. This is sort of the entire path we're talking about. And this is super nice because we have an approximation to the score. We can then just solve this reverse time SD to get a sample from P naught, right? So because this x sorry, the YT here will then be simulated from P naught, which is going to be equal to P data, hopefully. All right, so the main thing is just that we sample Y naught from this P big T, and then we simulate this differential equation. You have to solve it using a numerical solver, but at least we sort of have a pretty clear idea how to go about this. Any questions about this? No, then I move on. And so I said, like, if we can actually, so if we can solve this, and we can ensure that this is PT is equal to P prior, meaning that what I mean by this is just saying that we need this big T to be sufficiently large so that we actually get something that looks very noisy, right? If we just make T very, very small and we just add a bit of noise, it's still going to look like a data distribution. So we wanted to look something like, like a Gaussian, for example, like a isotropic Gaussian. How we can solve this ST? We're good. We have a way of sampling from this sort of a noise distribution to the data. We have a way of doing the denoising, that reverse process that we've been talking about. And so we're back to this kind of framework that we've been going through. The only issue is that, well, there's a couple of issues, I suppose, but the big one is that if we want to ensure that this is the case, as I said, the integration time needs to be somewhat large. I mean, large is probably, not talking like hundreds or whatever, but it's sort of like relatively large. We need to increase it to improve this property. And that means that we're going to induce a larger numerical error in the total solution to the reverse process, right? Because we're using numerical solvers. And so we're solving this backwards time, the reverse time SDE. If we're then sort of doing this over a larger amount of time, we don't do anything with the discretization steps, well, then we're going to sort of have a larger error. You can always like try to use higher order SDE solvers and so on, but this is more expensive and it's difficult to sort of figure out the sweet spot. But because of this, they also propose a way to sort of deal with this. And this brings us back to some like the Langevin dynamics that we talked about originally. This is actually one thing I want to point out is that this stuff that we've seen here, this, even though it's an SDE and Langevin dynamics is also an SDE, this is not Langevin dynamics, right? What we're doing here is we're sort of going from YT +1, or rather not +1, but we're going to some YT that is smaller, right? And so this, and Langevin dynamics was kind of more about finding samples for this thing, and then we just use the initial point, finding samples for this thing, and then we use the initial point of this to start a chain for this thing. And so this is, they sort of noticed this and they introduced this sort of more general predictor corrector sampling approach. And the idea here is that you have you sample from the endpoint as you did before, and then you iterate through the sort of the XIs in a reverse way. And then we have a predictor, and the predictor here is going to be the SDE solver, right? So we have an SDE solver that gives us an approximate solution to XI, right? At some T, say call it denoted TI. And then we have, and the idea then is that because this introduces numerical error, because we're using a discretized version of the SDE, we introduce a corrector, which is going to take this initial XI and then try to improve upon it so that it becomes closer to a sample of PT XT, which we in fact can compute. This is from like the forward process, right? This is what we take in the gradient perspective. And since we have Langevin dynamics, we only need the score, like the nabla of this log thing. And so we can then run, essentially, for example, we can put Langevin dynamics in here to sort of improve upon the sample that the SDE gave us. Right? So SDE solver gives us an XI. We go, hey, there's probably some numerical error in here because we're using a discretized version. And so we're going to use a corrector to sort of improve the sample and make it closer to a sample from this thing, PT. And then what we can do is we can use Langevin dynamics or like HMC, like some score-based things. And we run like this corrector for like M steps, right? So we run this MCMC chain for like some amount of steps. Usually in practice, people just do one as like a simple thing. Questions about this? Oh, good.
Just a quick question, Tor. Like normally these things would be run like in MCMC land with like wrapped in Metropolis Hastings with a accept reject step.
Yeah.
I guess that's just dispensed with because we've got no density under which to actually evaluate these things. Is that right? Or just got gradients?
Yeah, exactly. So you could compute this area in closed form, I guess, right? And you could compute maybe the PT +1. for this thing. You could maybe introduce like a metropolis and stuff. Could you not? Because you have a PT here, you can compute this because this is from the forward pass, right? This is
isn't the thing we want. If you thought about it, at least in the way that Vincent presented it, you'd need to integrate it, through the chains, and that would be have numerical error too. That would be like the forward pass from Gaussian noise through to data distribution, right? And you need to integrate through that process.
Could you not just like take the marginal here, like from the forward pass instead of the backwards pass? This is essentially what we're doing here, right?
Well, at least under Vincent's case, that would be an approximation because that would be the Qs, right?
Yeah, that's true. That's true.
I mean, maybe everything's a bit approximate here anyway, but
yeah. But yeah, like at least they don't use it. Let me put it like this. They sort of just run Longevin and they don't do any adjustments. They don't have like a metropolis stuff in there.
I see.
Yeah.
So sorry, I also just had a question. So for the loss function, you only look at the reconstruction at the very end. So you're not doing any kind of interim losses within the chain using this corrector.
Yeah. So this is after we've learned everything. So there's not doing anything with losses or anything like this. So this is after we've learned this S theta, right? And then this is approximating the sort of this quantity here. And then the corrector here is all it's doing is sort of using this quantity and then running sampling. Does that make sense? So it's like trying to sample from the distribution that's described by this score at the particular xt. Does that answer your question? Or did I
yes, I guess. Yeah. So basically, it's doing it in a fixed way, just given the score. So you're never training it to do it better.
Exactly. Yeah. This is after you train it.
Yeah, I understand. So, yeah.
Good.
Thanks.
No worries. And yeah, and so if you look at the variance exploding, remember this was the one from the I have forgotten was it SDLM? I forgot. It's like the score S score matching the denoising model. There we go. And then we have this denoising probabilistic model. Right. All right. So these are the VE SD corresponds to this thing, and the VP SD corresponds to this thing. And here they sort of put these into this predictive corrector framework. And so what we have this here is this predictive thing. And in this case, this is solving the SD that we found. And then we have this corrector term, which is just running Langevin dynamics for each of these two afterwards. And so you can view this, the original, like the SMDP method as just this part. So we like cross out this part. And the original method from DPM can be viewed as only having, no, sorry, I meant opposite. So the SMDP was without this predictor, right? It was only using Langevin dynamics. It was using a needle Langevin dynamics. It was slightly different in the sense that it would initialize the xi from the sample we obtained from xi plus 1, while the DDPM it can be viewed as without the corrector. There was no Langevin dynamics in there when we were doing the reverse pass, right? We were just trying to learn that. And so you can view it as this thing. So only a predictor, essentially. But so what we've done now is we've taken this SDE framework and they've sort of designed this predictive corrector framework for it. And they use both of these, and they can use this for both of these corresponding methods and improve upon them, as we'll see. And yeah, I was just demonstrating the same picture as before. Now we're doing the opposite, right? Going from noise to something that's not noise. And we can, so this far, the issues kind of with SDEs is that it's not easy to compute log likelihoods. So it's very useful for doing generation of samples, and we have done that very nicely, but we can't actually compute the log computation. We can't actually compute the log likelihoods nicely. But it turns out you can actually take an SDE and then convert it into an ODE, like an ordinary differential equation, which is without any noise whatsoever. So this is a completely deterministic process. So if you sample, and it turns out that this actually has the same marginal densities if you sample x0 from p data. So you sample your x0 from p data, and then you integrate this deterministic system, condition x0, and you actually get actually results in sort of samples from, so this xt will then be from pt. which is quite neat, to be honest. And it also means that you're now in the sort of the neuro-OD territory. And this is essentially like a continuous normalizing flow, because the solution to an order differential equation is. And so you can actually talk about computing the log likelihood using the sort of the standard it's like instantaneous change of variables. But essentially, it's just change of variables, and it's doing it at every step, and you have to integrate this thing. And again, like since we are approximating this thing, right? No, sorry, we're not approximating that, but we have this. This is a very simple thing in our case, and so this won't be like a huge issue. We'll only have to take the one partial derivative. It's not going to be second order long. But this is not something they use to train, right? It's just something that you want to do an evaluation afterwards. And this finally brings us, and sort of a final illustration here of like the different kinds of methods, essentially all put in one picture. So we have this forward SDE that integrates takes us from the data to some noisy distribution in the middle. And then we have this reverse SDE that takes us from the prior, like this XT here, to the X data. And then you can see these white lines. These are examples of the probability flow OD. So these are like very, very smooth solutions, right? But they also have the same marginal distribution for a given time. This is sort of all these different methods like kind of put in here. Like this is kind of full picture, I suppose. Is there any questions? Okay. So that brings us to empirical results. And this is kind of, it's neat to see that these methods are actually useful. But because I'm not super familiar with the generative modeling literature, I had to sort of figure out what inception scores are, or what FID scores are and stuff like this. And so from what I could gather, so if someone knows better than me, please correct me. It seems like the inception score is kind of, is the following, where you take essentially this p theta, right? This p theta is the process that we've defined using our score to sample from. So we have this s theta, and this implicitly defines this p theta going in which is this process that we had going from noisy data to the p data process, right? And so we sort of evaluate this by considering the KL divergence of the sort of classification probabilities conditioned on the generated sample X from our p theta and the classification, then the marginal probabilities of the classes. And this is under PI, which is like the inception V3 model, which is apparently really, really good at classifying images. And so the sort of the intuition here is that if our X, the generated data, is actually very similar to true observation, like true data, then this should be very, very informative, right? If the classification here is probability of it being a dog is very large, then this X there should be a condition on X, and the X there should look pretty similar to a dog compared to the model distribution. And this is kind of the idea. And so a higher inception score is good because it means that it's very informative for this inception 3 model. And then finally, we have also the I don't know, inception distance, which is.
Ask you a quick question, Thor.
Yeah.
Does the inception score say anything about memorization? Do you know?
Not that I'm aware of, in the sense like memorization of like in what sense?
Let's say your model can just reproduce your training data set. Will this give you a high inception score? Sorry if this is a tricky question.
No, I'm actually a bit uncertain. I'm wondering, like, because this inception model, I'm uncertain if it's like been pre-trained on, say, like ImageNet or something like that, like some other data set. So it's not actually using the same data set even. It could be the case. I'm not 100% certain. I would have to check that. Like, does anyone know actually? Probably someone in this call knows. No. Like the question is, like, does it say anything about memorization? Is like this inception score? Is inception V3 like V3 just sort of like a fixed model that people just pass around and like they use it on the new data sets?
Yeah,
or is this...
I know, I mean, with these generative models, there's kind of two things you want to look for, right? One, how photorealistic do they look? And then is this actually a new image or is this just from the data set?
Yeah, exactly. So I think, so the freshest inception distance kind of measures this in a sense as, well, no, it's not, because it's kind of, no, it doesn't actually measure that. Yeah, so I don't know the answer. I think there's a possibility that it's actually trained on a different data set. And so like the classifier is trained on a different data set. And so sort of memorization shouldn't really be an issue unless they include the same images. But yeah.
Thanks. If anyone else knows, please feel free to chip in.
Yeah, because I'm stepping on ice there. But yeah, and there's also this FID metric, which is here what they've done is they've fed all the data from like the original data through this Inception V3 model. They've taken the the pooling layer, like the very last pooling layer of this model, and they fit a Gaussian to it. They compute the mean and the covariance of the pooling layer on the data. And then they do the same thing, but now using 50,000 samples from the generative model. And then they look at the last line 2 distance between these two. And so both of these are like, they've there's some papers saying that, oh, these are very, these coincide well with what humans think about images and so on. So yeah, these are the sort of metrics that are being used. And here is a list of a bunch of methods. And the neat thing is that these sort of SDE approaches with a bunch of tricks and so on actually does fairly well, and they actually, they get to the level of GAN stuff, like GAN models. And so you have here you see the negative log likelihood evaluation, and also the FID scores. The FID score, the lower is better, right? Because the lower baseline distance between the data distribution and the generated distribution. And here you see the inception score and the FID score and CIFAR. As you can see, like, do you have these the benchmark is against these big GAN and style GAN approaches, where you can see that they actually do very, very well. And so I can maybe explain like the different methods here. So the DTPM here is the one that is using they've run the one that they had implemented, I suppose. And then there's the DTPM continued, continuous which means that they're using the SDE approach, and then we're solving the SDE. And then we have the different variance exploding, variance preserving and sub-variance preserving. And then the DD plus, the pluses indicate that they've gone the extra mile to try and really fine-tune the architecture that they're using and really mess around with stuff for a substantial amount of time, to the point where they can get optimal performance on these things. The overall takeaway from this is that it performs really, really well, both on these generative measures of quality, like the FID and IS, but they also do very well on negative likelihood evaluation, as you can see. So even though we're not directly optimizing for negative log likelihood, we're getting something that's really, really good compared to all these different approaches to doing which are all these density estimation problems models. Questions about this? Cool. And just a final note before we close off is that there's a very recent paper that we weren't going to include because it's very recent. Again, didn't get time to look at it properly, but it had a nice observation, so I had to put it in here. And this is that it turns out that for these SDE approaches, you can show that the KL divergence between the data distribution and the PF theta is actually upper bounded by the score matching objective, by this thing, and the KL between the PT and the prior. So the prior is like what we sample from when we want to generate data, and PT here is the end distribution of the forward process, right? And so we're saying is these are very similar. Essentially, this is what I was saying earlier. If this T is very, very, very large, then we then we can be pretty certain that it's going to look very noisy rather than the data distribution. And so then this goes to 0, and we end up with this being an upper bound on the actual KL. And so now it kind of makes sense that you get good negative log likelihoods too, because this is the minimizing KL is the same as maximizing log likelihood. And one thing I want to point out is that they have this weighted score matching objective, which mentioned earlier by Wenlin, and this is for a particular choice of weight. So if you choose the weight to be g of t squared, which is like the diffusion coefficient squared, then you get this bound, right? And so the point is that if you want to improve, and they show that also if you actually choose this particular choice of weight, which I hadn't done in these previous results that I showed you here. This was not using this weight. Then you actually can improve the negative log likelihood evaluation even further. And so you can run this score matching objective, which is this thing, but the denoising one, and you get something that's also optimizes for like an upper bound on the KL, which is super nice. But all in all, it's a pretty neat method. It's pretty cool stuff. But it's not as the sort of the flexibility of the method is maybe looks on the first glance a bit more than it really is. For example, you can't really use these arbitrary diffusion coefficient and so on. As we saw earlier, these are generally going to be like some scaling factor. This is generally going to be like some scaling factor of xt, and this is going to be some just like some fairly simple function of this t-value. You could use general ones, but then you have to sort of start messing around with solving partial differential equations and so on, which you probably don't want to do, and particularly not during training. And sampling is still slower than GAN approaches. So this is like a big thing. So it's quite slow to run this sort of backwards process versus what you do in GANs. And this is like this notion of like how large an integration time be to sort of get something that looks not very has diffused. And there's like a very interesting attempt at tackling this by Bortoli et al., where they use this notion of bridge sampling. So it's very cool approach, but didn't get time to go include it here. And yeah, there's probably some other drawbacks, but it's pretty cool that they can actually get I think one of the more new methods that can sort of get GAN-like generative model behavior. So that's pretty neat stuff, I'd say. And yeah, that's it. Thank you so much. Any questions to me, Wenlin, or Vincent?
There's one in the chat, or
oh, I can't see the chat when I'm sharing the screen. Can someone, Vincent, Wenlin, can one of you read it?
Yep, I can go. So the question from Matt: if the SDE version can be turned into an ODE, then why were the ODE version only used for the local likelihood calculation? That's the first question.
Yeah, so I think what they essentially saw is that like it's much smoother, right? And you end up with something which is much smoother. And I think they ended up just seeing that it was worse for the actual the generated samples. It's a bit unclear why, if I can remember correctly. Yeah, but the nice thing about the ODE approach is that you can very easily sort of control the error. ODE solving is much easier than SDE solving. But I think generally the reason is just that they saw that it wasn't really producing as nice results as the stochastic version. Yeah, I think that's my answer. But you should look at the paper to be 100% certain.
Could you? I think you may have mentioned this, but someone dropped into my office. The NLL tests here, are these all from propagating through the ODE, like the Fokker-Planck stuff you were showing? It's like the Fokker-Planck equation.
Yes, this is, well, it's not the Fokker-Planck equation. So this is Isn't that
what the equation for the density is, right?
Yeah. So so the Fokker-Planck equation is like of the SDE, right? So it's like looking at this thing. And you can solve this. This is what I meant, like it's not easily computable, because you could do it this way and integrate this thing.
Yeah.
But what they've done here is actually they've looked at the Fokker-Planck equation, and they've sort of messed around with it, and they realized that, hey, this corresponds to another SDE without any noise. Does that make any sense? So they sort of go through a bunch of steps, and they get to some part, they manipulate the sort of expression for the Fokker-Planck equation of the original SDE. And then they find that they can sort of identify this with the Fokker-Planck of another ordinary differential equation, like a noiseless version.
But isn't the Fokker-Planck an ordinary it's an ordinary differential equation for the
yeah. So what I'm saying is that
okay, there's some kind of transformation.
Yeah, this is not the Fokker, like this. What we see here is not the Fokker-Planck equation.
No, but in order to get to the bottom, you have to solve the Fokker-Planck equation.
But no. So that to get to the bottom, just solve this equation here. This is kind of the trick, is that they go to the Fokker-Planck equation. They show that you can actually, they identify that you can view this Fokker-Planck equation from the SDE as a Fokker-Planck equation of this ODE, and then you can just use this approach, which is just sort of integrating this. But this question, like, surely there's like some corresponds with the Fokker-Planck equation of this thing and this stuff. which I find a bit confusing. But this is just like using the standard change of variables.
Right. Okay. I would have thought that had to be a solution of the Fokker-Planck, but
yeah, I mean,
maybe-
they just. No, but I agree with you though. Like there should be some correspondence between it, right?
I presume it solves the Fokker-Planck because I mean, anyway, this is a bit of a side.
Oh yeah. Yeah, you're right. Yeah, of course it has to, right?
Yeah. So just for evaluating the NLLs, so this is the bit that I'm slightly confused at the moment. So F tilt, again, this is coming back to the slight worry I have about parameterizing gradients of log probs, and the constraints that a valid gradient of a log prob will have is not in the F bars here.
Yeah.
So can we trust the NLL evaluation here, in the sense that, is it possible that their method returns an F bar which is not consistent with any consistent gradient of a probability density, and therefore get non-normalizable values for log p of 0 out, and therefore skew the NLL results, because it isn't a valid density. It doesn't have to, if it pushes up density somewhere, it doesn't have to push density down elsewhere. That's like the kind of that it could happen to get. So do we know that that's not going on? Do we have any evidence that's not going on? It seems like an absolutely key question. So the inception score can be gamed, like Vincent was correct. Like the inception score can be gamed by memorizing examples, whereas the NLLs can't. If it's a valid density, if you push it up somewhere, you have to push it down somewhere else. So you pay a cost for predicting high density on regions in the data space. But if that metric can be gamed by them not actually having to correspond to a realizable density, do we have any evidence that it isn't memorizing stuff and cheating and putting up density everywhere and not having to normalize?
Yeah, so maybe this is related. So the lower bound that I showed later here, right? In this paper, they also mentioned, again, I have this paper I've sort of read once. I haven't properly digested it, but they also have a bound. This is one theorem. They also have a theorem where they bound actually they have a bound on the pointwise log density, right? And then they also show that for the example, the empirical results they do, they say that, this might not be. This is only holds if you sort of if this is satisfied and so on. So it's not like necessarily the holds, because we're using this approximation rather than the true thing. But in the examples that we ran, we could see that the point-based bound that we had was actually valid. That was valid across all the data examples, like all the examples they had. So in the empirical results, they could see that this upper bound on the negative log likelihood was actually what do you call that? Satisfied, even in practice. So maybe.
But to do that, they'd have to know what the underlying density was. Was this for toy data where they knew what the underlying density was? I mean, otherwise it's all with respect to estimates, which we think might be biased.
Yeah. That's a good point. This I don't remember, to be completely honest. I guess I agree with you. Like that does seem to this seems to be like a hole in that logic.
It'd be good to run this on synthetic data or something and make sure that it's doing sensible things with respect to ground truth. And it could be like a complicated, like a normalizing flow trained on real data or something like that, where we know what the actual NLLs are, and we could compare it to that density. We could even do other tests to
indeed. Indeed. I think also like it's. They use a particular infrastructure for like the particular network architecture, like something called UNets, whatever. But I'm uncertain I didn't look too much into what they actually are. I'm uncertain if they contain any specific constraints or whatever. I highly doubt it. Yeah, no, what you're saying is like a really good idea. It should be like more maybe toy experiment examples. There wasn't too many of them in the paper, as far as I can remember. Yeah, good point.